So I'm recording this part of the video because apparently the other part, the audio was very distorted, the last recording. I'm sorry for that. I will actually update the scalable learning site with this new video so that you guys do not get annoyed. Uh, so basically the last part of the lecture talks about thread context switching, and as a thread that has been scheduled to run on the processor and has acquired some resources, the thread can be evicted from the processor, can just leave the processor in one of two cases. The first one is basically a voluntary context switching. That is basically the thread itself deciding that it has had enough with the processor, or that it needs to block for some I/O or for some other thread to finish, and thus leaves the processor. And the other way is involuntary thread context switching, and that basically happens when there is something like an interrupt, for example. So let's talk about them in a bit more detail, starting with the involuntary ones because they are easier. And you basically need to evict from the processor if there is an interrupt that occurs with a higher priority compared to the priority that you have as a thread. And an interrupt with a higher scheduling priority will just kick you out, basically. That's one of the main reasons, or that is probably the main reason that a kernel thread will get kicked out. The other way is basically involuntary, where you basically get a processor exception also, and that would be basically, as we said, that the thread is trying to access some parts of the memory that it should not access, or is trying to access some devices that it should not access, and then the thread will be evicted and kicked out, and probably also terminated right away. These are the involuntary ways that thread has to go through thread context switching. But the other voluntary ways are basically through one of three calls that the thread itself can call. The first one is basically thread yield, and that is when the thread is waiting for some resources to become free, for example, or is waiting for some other thread to finish its computations, or is waiting for memory to be fetched from the from the memory of the computer, because memories are kind of slow, or is waiting even for something to read from the hard disk, a file to open, because file opening is very slow compared to, for example, the speed of the processor, as a file on the actual hard disk on a normal typical hard disk requires actually mechanical spinning of and motor spinning, and these are a few 100,000 times slower than a processor sometimes. And then you have thread join, where you basically, as a parent, decide that you will wait for your newly spawned children to finish, and basically call thread join, wait for that for the child to finish, and when the child finishes, then you can continue as a parent thread or as a parent process to do whatever you are doing. And then there is thread exit, which occurs when the thread itself decides that it is done, basically the program running in the thread, because a thread is, well, in essence, a program. And when the program itself finishes, it should call thread exit, and then, as we actually said, or in this figure, you basically are running and you're done, you go to the finished state through calling thread exit. So these are the ways that threads do context switching, basically. Then when you do a voluntary kernel thread context switching, the first thing that the thread or the operating system does, the kernel does, is that it saves the register of the old stack of the old thread that is going to be evicted, basically. Then switch to the new thread's stack and to the new thread, and restore registers from the new stack, because as I said that when basically you move from for example, running here to ready, you basically push your registers. I mean, you push your registers in doing that into the stack or somewhere. And the registers, as we said, are things such as your program counter. Your program counter is, you can think of it as a pointer that points to what line in the code are you running. So if you look at, I mean, you can think of it as basically, if you look at your code as basically a pointer that says that this is what is executing now, but on the hardware level. And well, it looks a lot also like when you're doing debugging, for example, then you have the debugger going line by line, for example. So it's not that, but it's just a hardware implementation of how to point to what are you doing right now. And this is, as we said, gets stored when the thread basically moves from running to ready, or even when it moves from running to waiting, for example. So the basically the kernel restores the registers from the new stack, where was the thread running, for example. And when the new thread starts, it returns not to the thread yield command. So the thread yield or the thread join command, for example, this is the last thing that you called before going to the ready state or before going to the waiting state, right? So you basically called something to go into that state. And when coming back, you should not go back to the same line that you called, which what you would typically do if you had, for example, an interrupt. But if you did not have an interrupt, then you basically want to go to the line after you called thread yield, because if you go back to thread yield, if the new thread gets scheduled here and goes back, the program counter points to the thread yield command, then the thread will just be pushed back again, so it will loop. So you do not want this to happen. So you should not return to the thread yield or the thread join line, rather to wherever the new thread needs to start, basically probably the line next to when you call thread yield. And this idea of thread context switching works for both kernel threads or user threads. I mean, it's exactly the same to the processor. When you're doing involuntary kernel switching, it's quite similar to what we discussed earlier when we were talking about what happens with with processes when they get interrupts, for example. And back then we basically talked about the process saving its state, and so on and so forth. And if you want to get back, this is starting from slide 21 and further in the kernel abstraction lecture. The main differences between involuntary kernel switching and a process switching, or even a user thread switching, is that if you're running as a kernel thread, there is no need to switch back to kernel mode, as you are already there. So I mean, you're already in kernel mode, so it doesn't make sense to try to go to kernel mode because you are there. And that means that you do not need to change the stack pointer, for example, because your kernel stack is kind of the same. And then if you are doing that and you're starting, you want to resume, you can resume any process on the ready list. It doesn't have to be the one that you just evicted. And the reason for that is that they're all kernel threads. You're running in kernel mode, and all of these are kernel threads. Of course, you might have some priorities in your threading, and in that case, you would basically start from a higher priority kernel thread, basically. And these are the main differences. So many people would actually note that there is a striking similarity between what we talked about when we talked about the process and what the thread does. And yes, that is true. And there are some differences, but these are operating system dependent. And we will discuss in later video how Linux basically handles threads and processes. In theory, the PCB should have more information about the processes at a space. So the PCB is basically the mother or the father or the parent thread, the parent process, and it should have more memory about what the whole process looks like, rather than just the thread, which is sort of a child that runs and basically does some things that is kind of limited. Okay, and that basically means that when you're doing context switching from one process to another, or basically doing kernel to user space switching, the right virtual memory mappings are stored in your PCB and not in your TCB, because your TCB is more limited. In most implementations, what basically happens is that since a thread is at the end of the day just a program that runs, and the process at the end of the day is just a program that runs, you have in your kernel's ready list a mix of both PCBs and TCBs. So you have both processes waiting to run and both threads and also threads waiting to run. Okay, and then you basically schedule whatever it is. And this implementation is not universal, so this is more the Windows way, where you have striking difference between what a process is and what a thread is. And that basically also means that, for example, process creation takes roughly 100 times more time compared to thread creation, for example, in Windows. And that's basically because a process is much heavier than a thread. And they usually call threads lightweight processes for Windows, for example. And you can find a few of the benchmarks that basically benchmark which marks starting a process on Windows and starting a thread on Windows. Linux has it differently, and we'll talk about this in the next video. This concludes chapter 4, and see you on Friday. Thank you, everyone.